Hello, everyone, and thank you for joining our webinar. And thanks for your interest in learning more about APECS, the new pilot line. And also thank you to the Swedish Chip Competenza for having us here. And yeah, as Sweden is kind of an exciting and interesting market when it comes to semiconductors and advanced technologies, yeah, we are very happy to have the opportunity to talk about APECS today. And so, yeah, so we'll give you a brief introduction on APECS, its technologies, the key innovations, and some general facts about our partners and the acting organizations, and eventually what service do we offer within APECS and how you can access them as a company or a RTO. And yeah, so the main question we'll try to answer today, and also which also reflects our mission, is how APECS leads the way in heterogeneous integration by providing diverse design capabilities, technologies, testing strategies for electronic components, and systems on a single platform. So this is both our topic for today and our mission and goal as APECS. So yeah, we were already kindly introduced, but just a few words about us. So I'm Felix. I work in business development within APECS, and I'm part of the research fab Microelectronics Germany, which is the FMD in German. And we are basically a cooperation between the Fraunhofer Group for Microelectronics and TU Leibniz Institute. I'm going to say a few words more about it in the following slide. And then we have my colleague, Erik, who's here. He's a senior business developer at Fraunhofer IZM, which is an institute based in Berlin, with like deep knowledge in microintegration, packaging, and related topics, and also a big contributor to the APECS Pilot Line. And Erik's gonna focus on the technical topics today. Okay, so a few words about FMD, the Research Fab Microelectronics Germany. So as mentioned, we are a cooperation of 13 Fraunhofer institutes and 2 Leibniz institutes, and that's gathered under one roof. I know Fraunhofer can sometimes be a little confusing and yeah, overwhelming, since we don't have like one Fraunhofer facility or one Fraunhofer institute, but we do have a headquarter, which is based in Munich. But on the other hand, we have around 74 institutes spread across Germany, focusing on different topics. So some institutes are focusing on biotech, others on security, software, others on material science, and but we do have 13 institutes all dedicated to microelectronics, and they are like grouped together, and together with 2 Leibniz institutes, we are kind of the main contact point in Germany for R&D and microelectronics, and also in Europe, basically. So there's around 5,400 employees, mostly scientists working within this corporation. We do have 13 clean rooms spread across Germany in like different institutes, with different key technologies like 300, 200 millimeter wafer processing and many other technologies. And I think what is important to mention is that we do applied science for industry. So we are application-oriented research organization. So we're deep into industry collaboration and technology transfer. And our business model is, so our budget is basically made of 3 columns. So we have a basic funding by the federal government of Germany, like an annual basic funding for our research activities. And then we do most of our budget through contract research and public customers like the European Union and the federal government. So this is how like our budget is basically made up. So as mentioned, there's 15 institutes within the FMD. You can see it here on the right side that they're like all over Germany. And we do have a business office, which I'm located at in Berlin, which like takes all the customer requests and acts like as a one-stop shop. And Fraunhofer IZM, for instance, also based in Berlin. But yeah, but we do have like other hubs like Dresden, for instance, which is a huge cluster in microelectronics. Yeah, I'm going through those points more quickly considering the time. Just maybe one other thing is that, as mentioned, you don't have to talk to each of those 15 institutes to ask for the services, but we do have a one-stop shop which you can reach and out to, and we can match you with the right institute. And on the other hand, I think it's important to mention that we offer customer-focused solutions. So we don't sell any like pre-developed products or like a big stack of services, but more like tailored solutions depending on customer needs and problems. And so we try to solve problems by choosing and finding the right technology stack. So back to APECS. I think you might have heard that there's 5 pilot lines now in the European Union. So we as Fraunhofer are coordinating the APECS Pilot Line, which is focusing on advanced packaging and heterogeneous system integration. And then we got 4 others. We got FAMES in France, led by Leti. We got Nano IC, operated by IMEC in Belgium. And then we got APECS Europe, the photonic pilot line that just kicked off this summer and is coordinated in Spain by ICFO. And last but not least, there's a wide bandgap pilot line in Italy, and just having his kickoff this month, I think. But even though there's like different technology approaches within these pilot lines, we closely work together. So we have joint work packages where we work together on different technologies, and also when it comes to access and services, we try to work together. So we have like a lot of contact and communication within those pilot lines. So as I briefly mentioned, APECS is coordinated by Fraunhofer. So obviously most of the work and the work packages are being done in our several institutes, but we do have many partners in Europe supporting APECS. So we are a consortium of 8 institutes, RTOs basically in Europe. So for instance, we got VTT in Finland, we have IMEC, Leti, the Technical University of Graz, based in Austria, and INL in Portugal, CNM in Spain, and FORF in Greece. So each of those RTOs are contributing to APECS in a certain way within a certain technology, based on their competences. So this is how we basically develop and build the APECS pilot line together. So before diving into the technologies and the actual key innovations of APECS, I want to talk briefly about the purpose of the APECS pilot line. So why did we eventually came up with pilot lines, and why do we need them? So I think many of you heard of the European Chips Act, which was published a couple of years ago. And the overall goal is to make Europe and European industry and economy more independent from suppliers from Asia, from United States, and those countries and regions, and to bring more chip development and more know-how and more infrastructure to Europe. And therefore, this Chip Act was announced, and also therefore we got those pilot lines to foster European R&D and industry when it comes to semiconductor innovations. So we are trying to establish state-of-the-art infrastructure for those technologies, which is chiplet technologies and heterogeneous integration in APECS. We are building technological capabilities for modern semiconductor devices. And this is also important. We are supporting, and so we're here for European industry. So we don't do the research and development for ourselves, but to help European businesses, RTOs, and industry leaders to be competitive, become more independent from as I said, Asia, United States, and to establish a supply chain in Europe. And lastly, we're trying to lead the way in advanced packaging and heterogeneous integration by providing technologies on a single platform. So that's our main goal. Okay, so now I'm handing over to my colleague who is going to guide you through the technical parts of APECS.
All right, And thank you, Felix, for handing over. So basically, why is APEX an immediate requirement for next generation semiconductor devices? That has to deal that a system on chip, a monolithic system on chip, will likely, with the advent of the end of Moore's law, a system on chip will not anymore be adequate for all targeted applications, and this is why the buzzword of more than Moore, aka known as heterogeneous integration, comes into play. And the challenges seen there are clearly about the involved design complexity, because you're not dealing anymore with just one silicon material, but we have to deal with CMOS, indium phosphide, gallium arsenide, silicon photonics, other 3.35 semiconductors. You have to manage electrical and optical coupling, ensuring the respective co-design with respect to efficiency and thermal stability. You have to look into standardization requirements, because these are really required for an industry uptake, and the PICS Europe pilot line will be addressing that in collaboration with the APECS pilot line, because in contrast to what we have seen in CMOS package integration in the past decades, this is where the photonic integrated circuits and the optical integration technologies, they really lag behind. And so when we look into these kind of heterogeneous integration, where these standardizing interfaces really match with the needs of the other pilot lines, this is clearly where we'll join forces. Also, manufacturing precision for high-density interposers and the integration capabilities is a requirement. So if you look to the most recent CMOS devices, which have 2 nanometer advanced nodes, or even right now going to 1.8 nanometer advanced nodes, their I/O density is also skyrocketing. You have to interface them with the legacy technologies, with also much coarser approaches for, say, for example, power devices or RF devices. So that requires that you control all the involved process variations. For sensors, you have to look into also stress-free bonding, and governed over all of these aspects are the testing concepts, because if you get bad devices out of the manufacturing, your cost management will run awry of your targets. So this means we have to improve yield, scale the automated assembly processes, thereby reducing also fabrication costs, and also minimize supplier dependency, especially from the Far East, trying to use processes which can be sourced from within Europe. And in order to do that, we have targeted three main areas of activity, subdivided into the design, into the chiplet integration, the chiplet fabrication. And the chiplet fabrication by itself is more about the modules for the chiplets, is about the chiplet integration platforms, which consist basically of advanced interposers, the functional integration, and the advanced packaging. That is dubbed here as well. So everything is connected through the design. STCO stands for System Technology Co-Optimized Design, because we have to integrate here the knowledge gained from the integration itself. So this one where we build chiplets, already doing that kind of heterogeneous integration on the front end, and providing chiplets ready for the subsequent merging to modules. Then the advanced interposers, which range from the established technologies for ultra high density on 300 millimeter silicon. We will advance this from currently something in the microns scale towards the submicron scale on these large areas. But we go and also to look into non-silicon interposers, like as required for high frequency, to photonics, to MEMS and sensors, which typically will be polymers, which will be glass. here, both on the 200 millimeters as well as into interposers based on glass core, on organic materials, and fan out, which go up to 600 millimeters. That should include also passive and active functionalities, which will then be integrated by the subsequent parts, but first being tested, characterized, and assessed with respect to their reliability before then finally integrating them into the modules. The upper part here, the functional integration with 3D stacking and the wafer scale 2.5D integration, that is taking place on the far end back end of line, while advanced packaging with high density assembly, embedding and fan out integration and so on. This is mostly what the currently known back end technology takes place. Now, all those developments clearly have to take into consideration the European Green Deal, because we want to be as eco-sensitive as possible while still retaining the cost advantages and the performance advantages for this heterogeneous integration. An illustration of the possibilities is given here in that sketch, which nowhere depicts anyhow a real module, but it shows that we will have a split between the integration at the wafer scale, as I mentioned, back end of line, far back end of line, and front end, as well as integration of substrate level, which may be the back end, but gradually moves over to the far back end of line as well. So here is where the two industries, which hitherto had been strictly separated, they start to merge. We have some examples picked out here, so I will run you through these animations, like, for example, photonic component integration onto a carrier with electro-optical interposers that lead then finally to an RF circuit for the wireless communication to the outer world. We will look into the integration of sensor devices, which can happen both on the front end side with what is dubbed quasi-monolithic integration, but clearly also on the far back end of line, where we'll mount the sensors together with ASICs and supplemental devices into an hermetic enclosure. We will also look clearly into what is now required for high performance computing or the AI data centers to the integration of 3D stacks that is done either by micro bump bonding as state-of-the-art technology, or by hybrid bonding, which is dubbed the next generation of ultra-high density integration for those stacks. The quasi-monolithic integration for CMOS devices, dubbed also CMOS Plus, will also see its role in here. And also we are looking into optics integration and also quantum device integration. And this is due to the fact that part of the effort here compiled in the APECS Pilot Line is founded also on legacy technology and also on the quantum neuromorphic computing facilities that has been established and has been absorbed by the APECS Pilot Line. So the key innovations we want to address here are the worldwide first chiplet integrated and highly integrated chiplet platform, which looks into 2.5D, so side by side, plus 3D, as well as pure 3D integration. And we will use multiple core technologies like CMOS, CMOS Plus, optical, high frequency, non-electric devices as well for sensing, for example, leveraging here the innovations of the advanced packaging. That is accompanied by a comprehensive end-to-end design flow, as well as this STCO methodology, again, system technology co-optimization methodology, for these kind of chiplet-based advanced heterogeneous integration platforms, which take into account also design for performance, design for yield, design for power efficiency, design for testability. I like the word DFX, design for anything. As briefly mentioned, there will also be a radical innovation, the quasi-monolithic integration. That's basically a layer-by-layer integration of functional elements already in the back end of line, as well as in the far back end of line, dubbed also advanced packaging. We will offer also prototyping for both the high performance as well for technologies which do not require these extreme performance capabilities for more legacy-oriented aspects of the European industries. We expect to have these kind of novel back-end-of-line interface technologies also for 3.5 wide bandgap devices for very high frequencies, combining that with co-packaged optics. And for all of that, novel testing concepts will be required to ensure that we really have a good output and a good yield. Looking into the industries we address in the first place, this is about the sensing technology, the medical instrumentation, industry electronics, telecommunications, but clearly also high performance computing as well as AI machine learning. We need to separate these two a little bit, albeit high performance computing pretty often is used synonymously with the data centers for AI. But we are looking also, say, for example, for industrial technologies or for the automotive sector into AI on the edge, where the sensors provide their information directly to a compute and memory system or a neuromorphic chip, which then will take a decision by its own. That is not a high performance compute, but it's a highly integrated and specialized device. This is basically where I would hand over to Felix again for the potential for industrial uptake.
Yes, thanks, Erik. So I'm taking over the third and last part of our presentation. I'm going a little faster because I want more or less keep our time. So we identified a couple of users that will be targeted within APECS. So first of all, we have the chip foundries that will be mostly approach of design services. So when it comes to chiplet design, for instance, then we got the integrated device manufacturers, IDMs, as well as the materials and tool supplier. And in general, semiconductor customers, meaning we offer to various type of companies and industries proof of concept, advanced prototyping runs, and especially small volume production. This is something how we distinguish from maybe the industry in general, because we are able to do very small volume test runs and productions for several customers. But we are also open to the research community, so granting access to researchers for the research to application transfer. And lastly, startups. So since there's many startups with innovative idea in the area of semiconductors and chips, but as you know, infrastructure for chip development is highly expensive and a huge invest. So we enable startups to run their business without having their own clean room by working together with our institutes. So we've talked about technologies in general, and now I'd like to give you a brief overview on what we are offering in detail. So we compiled a huge list of technology and services that are available or will be available soon. And then we put them in several categories, and I'd like to give a couple of examples. So the first category is surface technologies, including PVD, CVD, and related services. Then packaging and assembly. This is one of the key competences of Fraunhofer IZM. So direct wafer bonding and flip chip technologies, for instance. Third category, inline measurement. For instance, 3D surface metrology. And then we got CTR, so characterization, test, and reliability. It's always a kind of a strange word to pronounce, including RF characterization, for instance. Then we do chiplets and sensors. And lastly, design, as already mentioned. Design is a part of APECS STCO, and we have a design platform. And those are our current services. Not all of them available at this moment, but many of them coming soon or within the next 2 years. So it really depends on the particular service. So so some of you might wonder like how you can access those technologies. So as mentioned, we're trying to make the industry access as easy as possible, even though there's many institutes involved in APECS. So we do have an APECS website, apex.eu. We have a contact form, so you can submit your inquiries through our APECS website. Then me and my colleagues will receive this inquiry, have a look at it, evaluate it, and see, check the basic facts. We then set up an initial meeting with you, with a potential customer, and talking about the product, doing some Q&A, and discovering what is really need to do. And after discussing the details, we can decide, okay, which institute within the Fraunhofer Leibniz consortium is able to meet your requirements and to implement your project. And eventually you will have a detailed discussion with the institute on like conditions and project scope, and then you're ready for the implementation. So this is the process, and this is how our one-stop shop is going to work within APECS. So before coming to an end, a few announcements. If you happen to be at Semicon Europe, please stop by at our booth. There's going to be a European booth run by CHIPS.eu, CHIPS Joint Undertaking, and you will find all pilot lines present at this booth, and can stop by and have a chat. We will also have a STCO workshop, so focusing on design at Semicon on November 19, and you can still register for this workshop via this QR code. Next year we will have our first open access call. This is also part of the project, that we will develop a certain technology stack, certain technology packages, and then publish them next year in spring, and invite companies to apply with their project ideas for this certain technology stack, and then we can pick companies and do realize their projects next year. Also, we will have an APECS roadshow across Northern Europe. So we want to reach each ecosystem in Europe and present APECS to local industry. And we're planning to start in Northern Europe, especially in Scandinavia next year. So we will most likely stop by in Sweden somewhere next year. And last but not least, there will be a conference hosted by us, by FMD and APECS next year, September. So you will soon receive a save the date, but just for your information. Okay, so again, this is our consortium and our project partners. We're very thankful for being funded by the European Union and CHIPS.eu, and also by our federal government and our states in Germany, and by our partner countries. And thank you for listening. And we're happy to answer any questions you might have.